the Kenyan teacher here one more time. We welcome you to the second and final review of KCSE Chemistry Paper 1 for the year 2019. This is part 2 of Form 3 and 4 work. Welcome and be with us until the end of our short video. We begin this second part with question number 17. This question is borrowed from Form 4 topic, Energy Changes in Physical and Chemical Processes, what is commonly referred to as thermochemistry. Question 17. The heat of solution and hydration energy of potassium chloride is negative 17.2 kilojoules and negative 689 kilojoules respectively. We are asked now to calculate the lattice energy for the same substance, potassium chloride. So here, a student should know that actually heat of solution, that is delta H solution, is obtained by the summation of lattice energy, that is delta H lattice, and the hydration energy, delta H hydration. So, to get the lattice energy, we shall fix in our equation the values that we have from the question. Heat of solution, we've been told, is negative 17.2 kilojoules. The lattice energy is what we do not have, so we let it be lattice energy, and hydration energy has been given as negative 689 kilojoules. From here, to get our lattice energy, we will add 689 kilojoules to negative 17.2 kilojoules, and we get an answer of positive 671.8 kilojoules. It is 2 marks, half a mark for our relation, half a mark for replacing the heat changes mentioned in the question, a half a mark for the subtraction, and a half a mark for the final answer, totaling 2. We move on to question number 18. Question 18 is still from the same topic, energy changes in physical and chemical processes of Form 4. But this time, we are being asked about bond energies. Number 18. Use the information in Table 2 to answer the questions that follow. So bonds and bond energy. For CH, we have 412 kilojoules per mole. For ClCl, 242 kilojoules per mole. CCl, 338 kilojoules per mole. And lastly, HCl, we have 431 kilojoules. Let's now go ahead and look at the questions that were asked concerning our table. Part A. State what is meant by heat of reaction. Heat of reaction is simply the amount of heat energy, either evolved or absorbed during a chemical reaction. But between molar quantities of reactants. That becomes the definition of the heat of reaction for 1 Mach. Part B is where we were supposed to use the bond energies given in the table. So we are asked, calculate the heat change when 1 mole of methane reacts completely with excess chlorine in presence of UV light. So the first thing we were to do here is to write the equation for the reaction between methane, that is CH4, and chlorine gas. Because we have excess chlorine, we know from Form 3 work that all the hydrogens in methane would be replaced by chloride atoms. So our final product would be tetrachloromethane with that formula, and we shall have hydrogen chloride as well. So here, before we look at bond formation energies and bond breaking energies, we needed to have balanced our equation with a 4 on chlorine and a 4 on hydrogen chloride. So then, let's proceed to get now bond breaking energies. Bond breaking energies are usually endothermic because you need to supply heat for the bonds to be broken. So we start here. In methane, I need to break 4 CH bonds. So I'll multiply 4 by positive 412 because according to our table, each CH bond is accompanied by 412 kilojoules of energy. Why positive? Positive because we have agreed bond breaking is an endothermic reaction. This gives me positive 1648. I'm done with methane. So let me move now to 4 moles of chlorine. 4 moles of chlorine, I will have to break 4 Cl-Cl bonds. So again, I'll multiply 4 by positive 242. According to my table, Cl-Cl bond is accompanied by 242 kilojoules of energy in reactions which involve them. So doing the multiplication, I get positive 968. So if I do the total bond breaking energies, I get positive 2616. I move on now to bond formation energies. And before we proceed, a student should know that bond formation is an exothermic process. So our signs before our delta H is supposed to be negative. So I start here at tetrachloromethane. I'll form 4 of CCl bonds. Each CCl bond is accompanied by 338 kilojoules of energy. So this will produce negative 1352 kilojoules. Then for my hydrogen chloride, I will also form 4 HCl bonds. Each one of them will be accompanied by 431 kilojoules. So this gives me a total of negative 1724. Getting now the total bond formation energies, I'll have negative 3076 kilojoules. So now, to get my heat change, that is delta H, I need to do bond formation energies added to bond breaking energies. So this would be positive 2616. From it, I subtract 3076, and that gives me a delta H of negative 460 kilojoules per mole. It is 2 marks, so we shall give a half for the total bond breaking energies, a half for the total bond formation energies, a half for the subtraction or addition, and finally a half for the final answer, of course, together with the correct units. We proceed to question number 19. Question 19 is still from Form 4, but the topic this time is electrochemistry. Number 19. Given that the E naught of copper half cell, that is copper ions, is positive 0.34 volts, and that of zinc half cell, that is zinc solid zinc ions, is negative 0.76 volts. Draw a label diagram of the zinc copper electrochemical cell. So here we've always agreed more than once that the half cell with the most positive E naught, this time it is copper, most positive compared to this of zinc, becomes our strongest oxidizing agent. Okay? We know an oxidizing agent normally gets reduced. Reduction, on the other hand, takes place at the cathode of the complete cell. And finally, cathode we usually place on the right hand side of our electrochemical cell. This is what I call tagline, which is usually very, very useful when you are asked such questions. So, for purposes of complying with this rule, as we draw the two, copper will have to be on the right hand side. That means we begin with the zinc half cell on the left. So our diagram would look like this. We draw the electrode. This is zinc rod dipped in 1 mole of zinc ions. So we shall have here 1 molar zinc ions. You can use any soluble salt of zinc, and we make that to 1 mole concentration. Then here we will have our salt bridge, and we know the uses or the purpose of a salt bridge, which then now connects to the copper half cell on the right. So this would be our copper rod. Again, we make an electrolyte of 1 molar copper 2 ions. Then here we shall connect our 2 electrodes via a voltmeter. So this becomes our complete cell, and of course we shall label this as salt bridge. Now, how do electrons flow? Electrons normally flow from anode to cathode. So this would be the direction of electron flow. It is 3 marks. So a half a mark for labeling the zinc electrode, a half a mark for zinc electrolyte, a half a mark for showing direction of electron flow, half a mark for salt bridge, half a mark for copper electrode, and finally half a mark for the copper electrolyte. We proceed to question number 22. This is still from Form 4. Topic this time is radioactivity. Number 22. The diagram in figure 6 shows radiations emitted by a radioactive sample. So we have a concrete block to protect ourselves from the radiations. Then I have radioactive sample. I introduce electric field, the negative field here and positive field. Then M radiations get deflected towards the negative plate. N get deflected towards the positive. At this point, a good student of chemistry should know that M is alpha particles because they are usually positively charged, and that means they would be deflected towards the negative electric field. N, on the other hand, is beta because they are usually negatively charged. First question, identify radiations M. We've agreed it is alpha. Someone can use the symbol or we can use the representation, 42He, for 1 mark. N is beta, beta represented like that, or we can use the representation of 0, -1E for the next mark. Part B, explain what would happen when a sheet of paper is placed on the path of the two. So we know that beta will penetrate a sheet of paper, but alpha will be stopped. So the answer expected here is that the alpha particles will be stopped, while beta particles will penetrate the sheet of paper. So alpha particles being stopped, half mark, beta particles penetrating, half mark, total 1 mark. Next question is number 25 is shared between Form 3 and Form 4 work on qualitative analysis. This is identification of cations and anions. Chemical tests were carried out on separate samples of water drawn from the same source. The observations made were recorded in Table 4. So we have the first test, addition of aqueous calcium chloride, no white precipitate. Can we probably tell what is happening here? We know that because we didn't form any white precipitate when we added calcium chloride, then probably lead ions are not there, silver ions are also not there, and we also need to go for the calcium salts which are insoluble are also absent. This is the likes of sulfate, calcium sulfate, or even calcium carbonate. 2. Addition of dilute sulfuric 6 acid. There is no effervescence, but we form a colorless solution. So here, again, probably we are forming soluble sulfate salts. Then for the third test, addition of a few drops of acidified barium nitrate. We have no white precipitate. A good student should know that probably here sulfate or sulfite ions are not present. Lastly, we have addition of aqueous ammonia. White precipitate dissolves. This is obviously zinc. So we are being asked to state the inferences made in the reactions, starting with the first one. So on the first one, we added aqueous calcium chloride, and there was no white precipitate. Our inference would be lead ions, silver ions. These are chlorides that would have formed a white precipitate. And then for the calcium salts that would have formed a white precipitate, we have sulfate and we have carbonate as well. These we shall conclude are absent because there was no white precipitate. For test 2, addition of dilute sulfuric 6 acid, there was no effervescence. So here, carbonates would have produced an effervescence, sulfites the same, and even hydrogen carbonates. So because we didn't get any effervescence, these ones were also absent. Lastly, for test 3, addition of a few drops of acidified barium nitrate. There was no white precipitate, so sulfate or sulfides were as well absent, each for 1 mark. Next is question number 26 from Form 3, the topic being gas laws. 140 cubic centimeter of nitrogen gas diffuses through a membrane in 70 seconds. I want you to take note of the volumes. For nitrogen is 140. Then we are asked, how long will it take 200 this time round of carbon 4 oxide to diffuse through the same membrane under the same conditions of temperature and pressure. So here we will have to use the relation relative molecular mass of nitrogen gas by the relative molecular mass of carbon 4 oxide should be the same as time of nitrogen gas by time of carbon 4 oxide gas. But for this relation to hold, we always tell our students that volumes of the two gases must be equal. So in the question, we have different volumes. For that matter, we start by equating the volume of nitrogen to that of carbon 4. So easily, by arguing that if 140 cubic centimeter, this is for nitrogen, needed 70 seconds. Suppose we used equal volume with that of carbon 4, and that is 200 cubic centimeter. How much or how long would we have taken? So here, we shall have 200 multiplied by 70 divided by 140, and we get 100 seconds. So what we have done, we have now equated the volumes of the two gases. So as we work using our relation here, the time for nitrogen now will be 100 and not 70. Okay, so let's go ahead and put in our values. RMM of nitrogen is 14 by 2, that is 28. RMM of carbon 4 oxide is 12 plus 32, and that is 44. Should give me time of nitrogen, this time is 100, and what I don't know is time for carbon 4 oxide. Working out, I will have to square both sides to get rid of the root. So 28 over 44 should give me square of 100 is 10,000, and square of time of carbon 4 oxide remains this square. So to get time for carbon 4 oxide, I will need to find the square root of 44 multiplied by 10,000 divided by 28. And if we have a good calculator, we are supposed to get 125.35 seconds as our answer for 3 marks. Half a mark for equating the volumes, half a mark for putting in the values, half a mark for squaring both sides, half a mark for the root, half a mark for the final answer. And finally, we shall award a half a mark for determining the correct relation to use. Those are 3 marks for that question. Moving on to the next question. This is number 27. Number 27 is still from Form 3. Topic is nitrogen and its compounds. So we are asked, when burning magnesium ribbon is introduced to a gas jar full of nitrogen, it continues to burn, producing a green-yellow powder. Write an equation for the reaction between nitrogen and magnesium. This is quite easy. Magnesium solid, nitrogen gas, and we form magnesium nitride, which is a solid. Of course, we balance with a 3 on magnesium for 1 mark. Part B, explain why magnesium continues to burn in nitrogen but sulfur does not. The answer here is supposed to be that burning magnesium produces a lot of heat that is enough to break the nitrogen triple bond. Hence, it reacts or it continues to burn. While burning sulfur which is hot, produces little heat that is not enough to break the nitrogen triple bond. 1 mark, so enough to break half, little heat that is not enough to break another half. Total 1 mark. The space for that question was a little bit less, but we have managed to squeeze our answer. Lastly, for that question, we are asked to state one use of nitrogen. There are quite a number. One is in refrigeration. Second use is in manufacture of ammonia. We know the process is called Haber. And then we also have nitrogen being used in bulbs. We finally look at question number 29, which basically tested Form 1 work on apparatus, but we include it here because the candidate needed to have some knowledge from the mold of Form 3. Name an appropriate apparatus that is used to prepare standard solutions in the laboratory. This is quite easy. We call the apparatus volumetric flask for 1 mark. Up to that point, we are through with our review of the second part of Chemistry Paper 1 as tested in the year 2019. We thank you for your time, and please keep it here for more reviews, and don't forget to subscribe.